We got to the stage of recognizing why the symmetry is a direct relationship with the spectroscopic activity, and why then it will be able to be used as a predictive tool to correlate spectroscopic activity versus structure spectroscopic activity. Which means we need at this stage to reassess how do we treat symmetry, how do we look at symmetry from the point group point of view, and expand it until we know how to use all the features of a point group and not just something that is immediately recognizable. So how do we do this? First of all, it's important that we do not try to rediscover the wheel, because it can look daunting to think, oh, do I need to analyze everything mathematically speaking that is associated with this arrangement in space? Not really, because the point of the point group will be that since they can be derived and they are a classification system, everything that is associated with the point group is already tabulated, because the point group are a construct that is completely theoretical from abstract mathematics. The fact that the molecules fit into the framework of set point groups is one of the many beauties of nature, but it means that we can just use the mathematical construction available to us to then analyze everything that we have, because we already established that we can quite easily assign point groups to molecules and different configurations, different possible structures. They can get to their own point group relatively easily. So how do we know for every point group what is the list of operations and what is the mathematical correlation that they have with whatever is going on? This is what's in the character tables. So every point group has a table associated to it. It's not just the name, the code of C2V, whatever. It's a whole table with a whole description. So you have the list of the operation and the descriptors with mathematical modifications that can be done based on this point group. So how do we read the character tables? They look like something like this. You have them in your handout, so you can see how many different variations of this they are. But you read them always on the basis of they give you an indication of what is the point group. So you always know what you're talking about. If you go to a different point group, it's going to be a different business. Associated to the point group, there is a list of all the symmetry operations of the group. Notice how these things are not only the one that you used for classifications. So they are not just what you got from the flowchart. They are the extra ones that are a direct consequence of the fact that you identified the main symmetry elements. So from the flowchart, you get the main symmetry elements, you get an assignation of the point group. The assignation of the point group is right, the tables are going to tell you everything that is supposed to be inside. Then associated with this table, there is a lot of additional information, which are the symmetry species with the Mulliken symbols associated with this point group, the irreducible representation for every one of the symmetry species, and the Cartesian functions associated with all of these species. So you can see that some of these are rotationals, other are quadratic, and other are Cartesian. Okay? So this is how we build up this thing, but what does this actually mean? How do you get to a point in which a point group has a list of irreducible representations with a sequence of Mulliken symbols? Let's break it down one point after the other. So you assign the symmetry based on the relative relationship in space of the atoms in a molecule. But having something in space, because you see the arrangement of the atoms, relates to more than just you have atom, 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 because this means that the bonds are following this arrangement in space. The orbitals are following this arrangement in space. The dipoles are following this arrangement in space. The lone pairs are following this arrangement in space. So all that is related to this molecule from the point of view of a chemical entity is then following the symmetry that you know can be derived according to this molecule. So if with water that we know to be a C2V, and we can identify the C2V based on rotation and plane. We consider the normal modes. We can get the normal modes with the usual business that we've seen before. So from the total, which is 3n, we subtract 6 because we have a three-dimensional molecule. So rotational and translational degrees of freedom are going to be a total of 6. You have 3 atoms in water. So this is going to be 3 times 3 minus 6. This brings you to 3 normal modes of vibration. So 3 possible degrees of freedom that are not rotations and are not translations. Which one are those? Those will be the deviations from the resting symmetry. So the resting symmetry is this, and it's fixed. Whatever else you do around these bonds, which will be the vibration, will have to follow the modification from the point group, because you're not breaking the molecule apart, you are vibrating around the resting position. And this is the reason why this is called a degree of freedom. You can do it without disrupting the whole business. But when you do it, the molecule will look somewhat slightly different. So what are these modes of vibration? With water, since it's only 3 of them, you can actually derive them graphically, right? So you will have a symmetric stretch, so stretch out these bonds evenly. An asymmetric stretch, in which you stretch out this bond unevenly, so they're not both at the same time, one is shorter, one is longer. And you could bend these bonds around the angle. So instead of having these 104 degrees, you can bend them apart and change the angle. So these by notations are V1, V2, and V3. Or nu1, nu2, nu3, if you actually decide to read it from the Greek point of view. So these are things that you can do, and it's 3 of them, so you know you can do them, but they will go according to the point group. How do we classify this vibration according to the point group? This is done by looking at what happens according to the symmetry operations of the group if you do this. So if you have this motion going on, if you apply the identity, then whatever is going on here remains invariant, which means you could note this nothing is changing as a feature by putting a 1. So whatever you had before, there is a 1, is left invariant. If you apply to this, to a molecule in motion according to this asymmetric stretching, the rotation that we know water has, so the C2 axis, then you will flip this to this side and this to this side. The molecule, after the modification, will look like this. Before it looked like this. So it's flipped around. You can notice it, which means it's not 1, but it's -1. If you apply the first mirror, which is the mirror that contains the rotation axis, you get the same thing, because this is the plane of the page, so nothing is changing. So this thing is invariant. So the first sigma v will bring you to invariant. The second sigma v is the one that bisects away from the plane, and this will flip the molecule. So then you have a sequence of, you know that according to this C2V list of symmetry elements, identity is invariant, C2 is flipped, the mirror plane is invariant, the second mirror plane is flipped. Anything that behaves in the same way as nu3 has the same symmetry species of nu3. So anything that has the same invariant, flipped behavior would be like nu3 according to C2b. So he has the same symmetry species. So the effect of the operation is the thing that you call the basis vector. And this whole line of stuff is the irreducible representation of this whole process that you've done. So it is the representation of this whole process of, are you moving this thing around, what is happening, on the basis of a vector, 1, -1, 1, -1, or 0, and a list of representations. So this whole thing is called irreducible representations, because since they're a list of numbers that cannot be further simplified, this is what you get. This is what it is. So the most unique and concise way to describe what a motion is doing within a point group is by using the symmetry species. So this is the reason why they're special. And it doesn't sound very good to be like, oh, this is the effect of nu3. This is not very systematic. How do I know what am I talking about? How do I know if something else is doing the same stuff? For this, we can use the Mulliken symbols that I already introduced last time when we were looking at the orbitals. And the Mulliken symbols will assign something depending on how is your motion, how is your object behaving against the point group. So it's always related to the symmetry elements of the point group. If you go into a different point group, it's a different business. So in this case, nu3 is antisymmetric around C2. It doesn't have another axis that is not C2. C2 is the main and is the only one. But from the main mirror, it is symmetric. So if you look at these pieces, antisymmetric with respect to the principal axis, symmetric with respect of the mirror, you end up with a species that will be named B1. So this antisymmetric of the principal axis of symmetry is the B, and there is nothing that goes the one in perpendicular. There is nothing else. So this is telling you all of these features by nature of telling you B1. What do I mean? I mean this. You know it because the definitions is this. So whatever behaves in the same way behaves like B1. This is how you build it in the table. And this, I wanted to refresh again, is also the reason why you give labels to the orbitals. So the orbitals have a name according to where do you place your crystal field. So your stuff in octahedral crystal field is labeled e.g. T2G, but why? Because EG is this 2, T2G is this 3. So this is telling you, you have a double degenerate and a triple degenerate configuration. Both of them are symmetric with respect of the center of symmetry. And the 2 that you have in this thing is this thing that is telling you, you have this feature around the axis. So if this is your principal axis, this thing is anti-symmetric with a C2 that is going in perpendicular, because otherwise you wouldn't have this thing that flip around the planes. So e.g. T2G immediately tells you what is going on with these orbitals in comparison to the geometrical arrangement. Please notice that the labels will change according to the symmetry. And I've noticed that the tetragonal crystal field has only these T2 and E. Please give a thought of why would you have T2 and E instead of EG and T2G when you go into tetragonal crystal field. Sorry, tetrahedral crystal field. So the tables, when you build them up, they provide you everything that can be done within the point group that only goes according to motions that are allowed. If you were to do something that doesn't follow one of these, you're not doing something that can be done without breaking the point group. Note, though, that unlike the derivation of what does nu3 do as a symmetry species, these things are tabulated, which means we do not have to calculate them, we do not have to memorize them, we don't have to remember which symbol means what. We just need to open the table, read the tables, and behave accordingly, because we know that the mathematics will fit and will keep the whole cluster together. So if we assess again the normal modes of water based on the symmetry, we know that these three modes must fit into something. So we derived nu3. You can check if you can get the derivation of nu1 and nu2. But nu3 is B1. Nu1 and nu2 are both in A1 species. So the asymmetric stretch and the the symmetric band and the symmetric stretch are two A1 modes. The asymmetric one is the B1. This means that you can express this gamma vib of the notation of the normal modes of vibration of this molecule is equal to 2 of the A1, 1 of the B. This tells you that these three modes have this arrangement, not another one. They're not three different symmetry species. Two are the same and one is different. So since the symmetries and these normal modes of motion have a correlation in space, they are associated directly in the table with a function. So something that will correspond to this motion in space. So this correspondence is the one that you can use to know, is this motion fitting or unfitting with the selection rule of what is going to be an absolutely physical process, which is spectroscopy. So you shine infrared or you put the laser to do Raman, which one of these is going to go according to the selection rules. So in the Raman active, you must have a change in the dipole moment. Sorry, in the Raman active, you must have a change in the polarizability. In the infrared, you must have a change in the dipole moment. This means that you must have an XY component in the infrared and a product feature, so something that is multiple times a Cartesian axis in the Raman. These are the modes that we know are there. And you can see that this one is a Z component. This one is an X component. This one is an XZ component. This one is all the possible square products of the axis. This means that in water, all of the possible vibrations that you have of this OH group and what the hell is doing will give you both a Raman active and an infrared active behavior. You will see them in Raman, you will see them in infrared. The tables are telling you this. Is this experimentally proven? Well, this is an infrared spectrum of water. You see two stretching bands. They are a bit overlapping with each other, but you can get the suggestion that these are two peaks because it would be too broad. And one sistering band that appears. On the other hand, if you do Raman, you will see the sistering band and the two bands in stretching. You can notice how they're a bit more defined as being two bands in the Raman. They are the same. It looks exactly the same because, as we said, both of them are Raman and IR active. So we know already from the symmetry analysis what we're supposed to see in the spectra. And whatever we see in the spectra, we can correlate back into, is this compatible with the molecule that I think I have and that I'm supposed to have? Because these will go one to the other. So if you don't know the symmetry assignation, then you cannot reverse engineer back with what is this telling me on the structure, but you can get a predictability on if this is my structure, then it will be doing this. If it's not doing this, then it is not my structure. But how can we get to a point in which we can do all of it without having to derive the symmetry species by hand for everything? We're going to see it in the next part and the final part of this lecture.